Okay, hopefully everyone did well on your previous test, the first test that we had on chapters 1 through 3. You're ready to get started on this second unit, and we're going to begin the second unit by talking about probability in chapter 4. And this first section is very much an introduction to probability because some of you may have not had a lot of probability in the past, and so we want to just take some time to be introduced to that. Okay, so like I said, this section 4.1 is just going to be basic concepts of probability. Okay, the one thing that I want you to take from this entire chapter is how to interpret probability values, because that's what we're going to take with us throughout the course. So it's important to understand that a probability value is going to be between 0 and 1. The closer it is to 0, the less likely it is to occur, and the closer it is to 1, the more likely it is to occur. And in having said that, you should be able to recognize that, like, if I'm asking for a probability value, you're not going to give me a value like 1.5 because 1.5 is never going to be a probability. So some definitions here in this chapter. An event is a collection of results or outcomes of a procedure. A simple event is an outcome or an event that cannot be further broken down into simpler components. And then the sample space for a procedure consists of all simple events. And that's just a listing of those simple events. So I want to look at an example here with this. If we have an event here, then our event might be, if we're talking about a single birth, our event might be having a girl, okay? Or it might be having a boy. Those are examples of simple events. And so because of that, if we wanted to list those out, then our simple events would be either having a boy or having a girl. Those are the events themselves, the simple events. The actual event itself would be having a child, and then the possible outcomes for that would be the boy or girl. If we're talking about having 3 births, our event might be that we're going to have 2 boys and 1 girl. But because there's different ways for that to happen, you could have a boy, and then a girl. You could have a boy, a girl, and a boy, or you could have the girl first and then a boy and a boy. So this is the event itself, 2 girls and 1 boy, or sorry, 2 boys and 1 girl. And the simple events that make that up would be these 3 here. Okay, so if we were to list all of the simple events for 3 births, then this would encompass all of that. Some of you may be familiar with the tree diagrams. With the tree diagram, you start at the top from a point. And having your first child, you could either have a boy or a girl. And then for the second child, you could have a boy or a girl. And another one would be a boy and a girl. And then if we have our third child, it would be a boy, girl, boy, girl, boy, girl, and boy, girl. So looking at this, if I were to list my sample space, I'm going to trace each one of these tree branches. That's why it's called a tree diagram, is because we have all these branches that we can trace down. So if we trace these down, that would give us the boy, 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 and then boy, boy, girl. And then we'd have boy, girl, boy, and boy, girl, girl. And then we could do girl, boy, boy, moving on to the second side of the tree. Then we'll have girl, boy, girl, 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 boy, and finally girl, girl, girl. So the tree diagram is a way to kind of give us an overview, a graphic organizer, so to speak, for listing out our sample space. Okay, so an example of a simple event, when we roll a die, the outcome of a 5 would be considered a simple event, but getting an even number would not be a simple event because this could be broken down further. There's different ways we could get an even number, and therefore that would not be a simple event. But getting a 5 can't be broken down any further, so that would be a simple event. And we just talked about the fact that 2 girls and 1 boy would not be considered a simple event because it can be broken down into further events, further simple events. So notation for this section, the capital P is going to represent probability, and then your capital letters like A, B, and C are going to be specific events, And then if we want to find the probability of one of those, then you combine those together and you'd have the probability of event A. Okay, here's a spectrum kind of to show you all of the probability values are going to be between 0 and 1. And if that's the case, here in the middle is going to be a 50-50 chance. Closer it is to 1, the more likely it is. Closer it is to 0, the less likely. And if it is 0, it's considered impossible. And if it's 1, it's considered certain. I would say that be careful on your calculator for things that look like this. So this is 1.25, and the calculator will put it as e negative 4. So this is 1.25 times 10 to the negative 4th, which is, this means move my decimal 4 places to the left. So it would be something like this. So what tends to happen is this could be a probability value. But what I see people do as far as giving an answer is a lot of times they'll just take this part and give that as their answer, and that is not going to be a probability value. 1.25 is never going to be a probability. 0.000125 would be a probability value. So be careful in understanding what the calculator is telling you with this and interpreting it correctly. Okay, so just kind of highlighting some of this, they have to be between 0 and 1. 0 is an impossible event, 1 is a certain event. So here's some examples that can never be probability values. This one is negative. This is an improper fraction. So anytime I have an improper fraction where the top is the numerator larger than the denominator, then that's not going to be a probability. This one's greater than 1, so it can't be a probability, and this one is negative. If I had, talking about the fractions, if I had 67 over 98, that would be fine, but 98 over 67 would not be because this one is more than 1. Okay. All right, so looking at 3 different approaches for finding probability. The first one is called the relative frequency approximation of probability. This one is based on observing a procedure and counting the number of times that it occurs. So if I'm looking for the probability of event A, I can kind of look over a period of time and see how many times event A occurred out of the times that the procedure was repeated. And that's going to give me a relative frequency approximation for the probability. An example of that, if we wanted to know like the probability of Wingate students having COVID-19, then we would look at like the number of positive tests divided by the number of Wingate students, and that would tell us the relative frequency probability that a Wingate student would have COVID-19. So that's kind of where you look at a procedure and count the number of times something has occurred, and that gives us a measure of the probability. Classical probability is the second approach here. One thing you have to keep in mind with this is that your outcomes have to be equally likely. So on the one we were talking about with COVID, it's not equally likely that somebody has COVID and doesn't have COVID. So that would not be a good case for classical probability. Classical probability tends to be like flipping a coin, flipping or rolling a die, things of that nature where like having children where it's a boy or a girl and they're equally likely to occur. So an example here, I have like rolling a 6. The probability of that would be 1 out of 6. And you're looking at the number of 6s divided by the number of possible outcomes. But because these are equally likely, we're able to do it this way. Okay, subjective probabilities, these are a little bit more vague, and it is just some kind of estimate using the knowledge of relevant circumstances. So some examples of this would be the probability of putting a man on the moon. Obviously, there's a lot of things that play into something like that, and so there's a lot of things that can affect the probability. So it is a subjective probability or an estimate. Probability of dying in a plane crash, probability of getting stuck in an elevator. So these are things that have a lot of things that are influencing the probability. It's not a clear-cut probability that we're calculating. We're really not going to do a lot with subjective probabilities, but I did want to mention those. Sometimes none of the approaches are going to be the best approach. So sometimes you just have to simulate the procedure. It's a process that behaves in the same way as the procedure itself, so similar results are produced. So a lot of times we find our probabilities through the simulation process, and we're not going to work a lot with simulations during this semester either. Okay, rounding probabilities, here's another rounding rule for you. And the rounding rule is basically this. If you have a simple fraction, and by simple fractions, I mean things like 2/3, 5/9, 1/2, 1/3, things of that nature where your numbers are less than 10, then you can leave it as a fraction in those cases. If it gets any bigger than that, then I would say go ahead and convert it to a decimal. Decimals are actually easier to understand than fractions when it comes to comparing probabilities. And we're going to do a lot of that. So the decimal is in a lot of cases going to be your better way to express this. If you're putting it in a decimal form, you want to give it to 3 significant digits. And I'm going to talk about significant digits here on the next slide. Okay, so like I said, if you've got some simple fractions, it's okay to leave those as fractions. Some kind of unfamiliar fraction, you want to convert it to a decimal, and we're going to round it to 3 significant digits. So if I look at this one, if I'm doing 3 significant digits, these first two don't count as being significant because they're zeros. So it's not that it's a zero necessarily, it's got to be here in the beginning and be a zero, and those are going to be considered insignificant. So this is going to be my first digit, second digit, and third digit. So I want to round it to 3 significant digits. So I'm going to look at this number, and because it's less than 5, that means I'm going to it's not going to round it up, and it's going to stay here at 00259. So these are my 3 significant digits that I want to show as part of my answer. If I look over here, these are not considered significant because they're zeros. Here's my 3 that I want to round to. And if I look at this, because this is greater than 5, it tells me that I'm going to have to round up. So this 69 is going to round to 70. So there's my 3 significant digits that I want to give as my answer. If I had 0.03098, then this one would not be counted as significant. This one actually would be significant because it's between 2 values here that are non-zero. So when I go to round this, I'm going to round here. This 8 means I'm going to round this one up. So I'm going to be at 10. So these are my significant digits that I'm showing here. Okay, the law of large numbers is another concept that you should be familiar with as we get started. As a procedure is repeated again and again, the relative frequency probability of an event tends to approach the actual probability. So I want you to think about, we're all kind of living in the middle of this pandemic with COVID-19. So early on in this pandemic, there were not a lot of cases. So it was really kind of hard to get a grasp on what the death rate for COVID-19 was. Some were reporting it higher and some lower, and it was just kind of all over the place. But through this law of large numbers, as the amount of people getting sick with COVID-19 and then start looking at the death rate for those people, we've been able to better establish what the actual death rate is for the COVID-19 virus by looking at this law of large numbers and looking at, as we repeat the procedure over and over again, of people continuing to get sick with it, then we can look at that and see kind of what it's going to approach. And as it approaches that, that's approaching the actual probability or the actual death rate for the COVID-19. Okay, so a couple things to keep in mind with the law of large numbers. The behavior is, we're looking at behavior over a large number of trials. So it doesn't apply to one outcome because one outcome is not going to, it's not going to have that averaging effect that the law of large numbers will. And then we should not assume that the different possible outcomes are equally likely when we're talking about this. Okay, so here's an example of relative frequency with skydiving. We want to find the probability of dying when making a skydiving jump. And I really didn't intend for so many problems to talk about dying today, but this was some examples that I came up with here. So this one, in a recent year, we had about 3,000 skydiving jumps, and 21 of them resulted in deaths. So if we use the relative frequency approach, we're going to look at the number that actually died divided by the number of times they jumped. So 21 out of 3 million gives me this probability. So this is a very small probability. It's very close to zero. So we would consider this to be very unlikely that people are actually going to die doing the skydiving jumps. And just to mention, the classical approach could not be used here because the probability of dying and surviving are not going to be equal to each other. Okay, here's one example on texting and driving. In a study of U.S. high school drivers, it was found that 3,785 texted while driving during the previous 30 days, and 4,720 did not text while driving during that same time period, and it gives the reference here. Based on these results, if a high school driver is randomly selected, we want to find the probability that he or she texted while driving during the previous 30 days. So we're looking for the probability that they text while they were driving. Okay, so when we look at this information here, we found that 3,785 of them were texting, and we need to know how many that's out of. So we had this many that were texting and this many that were not texting. So we need to add those together. And when I divide that out, that's going to give me the probability that I'm looking for. So the total there is 8,505 for the total number of drivers. So the ones that were texting was 3,785. We'll divide that by the 8,505. This is obviously not a fraction we're familiar with, so we want to go ahead and convert it to a decimal and round it to 3 significant digits. So it's actually, when we look at this in comparison, remember 0 is impossible and 1 is certain. So we're actually pretty close to right here in the middle, that it's about a 50-50 chance that these teenagers were texting while driving. Okay, complementary events. This is a term that you'll hear us use throughout this chapter, especially. A complement of event A, we use this little bar over the top to represent that, and it consists of all outcomes in which event A does not occur. So if I said the probability that someone is a freshman, the complement to that, okay, if I wanted to look at its complement, that's going to be everybody that's not a freshman. So that's going to be the sophomores and the juniors and the seniors. And we could even throw in the graduate students. So everybody that's not a freshman is going to be the complement to the freshman. Okay, this is kind of a Venn diagram showing if it's an event A, then everything that's not in A is its complement. And so because it's either in A or it's not in A, the two together combine to be a certain event. So it's certain that it's either in A or it's not in A. And because of that, we have the probability of A plus the probability of the complement of A is going to equal 1. And we can manipulate that around and find that the probability of the complement is 1 minus the probability of A, and so forth with that. So if I know the probability of one of the events, I can easily find the complement to that, the probability of the complement to that. So if the probability of A is 0.25, then the probability of its complement is 1 minus the 0.25. So we're going to have 0.75 as the complement. So if I know that the probability of the complement is 1/3, then the probability of the event is 2/3. So they're going to add up to 1 regardless. Okay, so here's an example with the skydiving and the complement. So we found the probability of dying when making a skydiving jump. But if we want the probability of not dying, which would be the complement to that, we can look here. And we can either go straight and figure out the probability of not dying, because if 21 did die, then that leaves this number that did not die. So that divided by 3 million gives me this as my probability of not dying. Another way to think of that is the probability of dying. We found on a previous screen was 0.000007. So the probability that they're not going to die is, which is its complement, is going to be 1 minus the probability of dying. So 1 minus this is also going to give me the same answer. So it's just two different ways to look at approaching this answer here. Okay, so the rare event rule for statistics is it's one of those rules that's a little bit wordy and a little bit hard to understand at first, but it is very, very fundamental to understanding the rest of this course. So the rare event rule says if under a given assumption, the probability of a particular observed event is very small and the observed event occurs significantly less than or significantly greater than what we typically expect, with that assumption, we conclude that the assumption is probably not correct. So this is an example that I came up with here. When testing a vaccine for COVID-19, researchers work under the assumption that it doesn't work until proven otherwise. So when they start out, they assume that the vaccine does not work, and then they have to get evidence that it does. So, for example, if the number of people testing positive for COVID in their study is significantly less than for a group of similar size, so it's significantly less than what we would expect for the general population, so much so that it is actually considered statistically significant that it's that small of a number, then our options for explaining this are that either that was a very rare event and we just happened to have a sample where that few of people came down with COVID, or that our vaccine has to be working. So those are kind of our ways of explaining having a group with such a small number of people that are testing positive for COVID. So looking at this, it's either going to be occurring by chance and be a rare event, or the vaccine is going to be working. And typically we use 0.05 as like the cutoff. If something is occurring, and we talked about it being statistically significant with the 0.05. So if something's occurring less than 0.05 of the time here, then that means it would have statistical significance, meaning that it is such a rare event for it to have happened that it must be that the vaccine is in fact working. We'll continue to revisit this rule throughout the semester, and I think this is kind of where we look at it in a very vague and general form, and then we get more specific as we go through the course. Okay, this is kind of another example to help you understand. If we flip a coin, we assume that our coin is fair and that it's got a 50-50 chance of being heads and tails. So if that were true and we flip the coin, we'd expect to get some kind of sample space that looks like this. So we'd have a good mixture of heads and tails. One doesn't really appear to be dominating. And so that kind of justifies that our coin is a fair coin. But if we get an outcome that looks like this, then we have almost all tails with just a few heads. So either we were very unlucky and got the one chance out of like the one chance that this might happen in like millions of trials, or our coin was not a fair coin. And so if this is rare enough, then we'll just have to conclude that the coin was not a fair coin in being flipped. Okay, as far as how we use all this, using probabilities to determine when results are significantly high or significantly low, we use this 0.05 as the cutoff. So X is considered to be a significantly high number of successes if the probability of getting X or more is less than or equal to 0.05. And again, this can change depending on what we're talking about, but 0.05 is kind of a good guideline for determining if something is, sometimes we'll hear it referred to as unlikely, sometimes we'll hear it referred to as significantly high, or significantly low, and so forth. So the probability of X or more is got to be less than or equal to 0.05 to be significantly high. And in order for X to be significantly low, the number of successes is considered to be significantly low if the probability of X or fewer is less than or equal to 0.05. So basically we want the extremes, either higher or lower on the extreme, to be less than or equal to 0.05. I do understand this is kind of a difficult concept to wrap your head around at this point, and I just want to get it out there in front of you again for the first time so that as we develop this concept throughout the rest of the course, hopefully it'll start becoming clearer to you. Okay, so just a review of the concepts we looked at today. The probability of an event has to be between 0 and 1. 0 is an impossible event. A certain event is going to be equal to 1. We've got our notation for the event and then a notation for the complement. Okay, I have just a couple examples here. The first one, if we're going to use a table to find some different probabilities, the first thing I would suggest doing is totaling the table in each direction. So here if I have this as my original table, I want to add going across, add going across, add going up and down, and come up with this total here. So I have 98 total values included. This is a good time to become acclimated to these polygraph test charts because you're going to have several problems that deal with these. One thing to keep in mind is that your false positive and false negatives are always going to be on a diagonal, and your true positives and true negatives are going to be on a diagonal. You're never going to have two false that line up in a straight line or two trues that line up in a straight line when you're setting these up. So a false positive is when you get a positive test result, but the person actually did not lie. So that's considered to be a false positive. A true positive is when you have a positive test result and in fact they lied. So that would be an accurate representation. The true negative is going to be when you get a negative test result and they did not lie. So this would be another accurate representation. The lied but a negative test results gives us a false negative, so this would be an inaccurate representation. Okay, so if we want to find the probability of a positive test result, we want to look and see how many positive test results we had. And so in looking at this, we have 57 out of 98 for that. And if we go and divide that out, 57 divided by 98 is going to give us 0.558. Okay, the probability of a negative test result is going to be 41 out of 98. And I'm going to write that over here is going to be 0.418. Notice I'm rounding these to 3 significant digits. These happen to also be 3 decimal places, but 3 decimal places and 3 significant digits will not always be the same. The probability that they did not lie. So looking at that, we have 47 that did not lie out of 98. So 47 divided by 98 is going to be 0.480. Then the probability that they lied, there was 51 of those out of 98. So 51 divided by 98 is going to be 0.520. Okay, so those should be your answers to a problem like this. So the strategy here is to add across, add up and down, and get your totals, and then the problem's pretty easy from there. And so these are just some of the answers you should have given. Okay, last problem here. Looking at a deck of cards, I feel like you have to always have a deck of card problem, but I'm not going to hold you responsible for knowing the makeup of a deck of cards. So in a deck of cards, you've got 4 suits, you've got hearts, clubs, diamonds, and spades, and within each of those you have 13 cards. They go from 3 through 10, and then a jack, queen, king, and an ace. We have a total of 52 cards. So if we look at these, we're going to work through these. The probability of a jack If we look at this, there's 4 jacks out of 52. And I'm going to go back and convert these to decimals in a few minutes. The probability of a 6 of clubs, there's actually only one card in a deck of cards that's a 6 of clubs. So that would be 1 out of 52. If I look at a 3 or a 6, there's 4 3s and there's also 4 6s. So I'm going to have 8 out of 52. The probability of a heart, club, diamond, or spade, it has to be one of these. There's nothing else. So that's all 52 out of 52, which means 1. So it's a certain event that it's a heart, a club, a diamond, or a spade because there's nothing else left. And then this last one, the probability of a heart or a jack. If I think about it, there are 13 cards that are hearts, and there are 4 cards that are jacks. But there's one card that is both a heart and a jack. So it's getting counted in this group and in this group. So I need to take that away and then divide by the 52. This is actually using the addition rule that we'll talk about next class. So that's going to be 16 out of 52. And these are not common fractions, so I would expect you to go ahead and convert those to decimals. So these are the conversions for all of those decimals that you should have had. And that takes us to the end of this section on probability. If you have any questions, please let me know, and hope you have a great day.